Hello everyone, my name is Aleksey Generozov. I'm a graduate student at Columbia, and I'll took the liberty of changing my title a little bit because I'm not quite going to tell you where they are, but I'm going to try to address the question of, is it possible that they are hiding, without necessarily telling you their hiding place. But before I jump into my talk, I want to give credit to the rest of my group. So in particular, I'd like to highlight Petr Mimika. Later on in this talk, I'll be showing simulations of radio light curves from jets, and that's all Petr's work. Okay. So first, I'll start by giving some observational background on jetted tidal disruption events. So one such example is Swift 1644. In this event, we see hard non-thermal X-rays with rapid time variability at early times. And then later on, we see radio emission. And this is somewhat analogous to a GRB. You have some prompt emission and then radio afterglow from interaction of the outflow with the surrounding medium. So let's focus on the radio observation. So this is the radio light curve for Swift 1644 at 5 gigahertz. And let's also look at some radio upper limits from other tidal disruption event candidates. And so looking at the upper limits compared to the radial light curve, they fall well below that. And so the obvious explanation for this that should jump into your head is that, well, you know, of course this is on axis and maybe these are off axis events, and so they're much dimmer, but this is already quite late in the light curve evolution, and we expect this time the jet should have slowed down to non-relativistic speeds and should have isotropized. And so we don't think viewing the jet off axis could significantly suppress the emission. So this is pointing to an apparent dearth of powerful jets and other tidal disruption event candidates. Now we've been hearing a lot about this particular tidal disruption event, Assassin 14Li, and for the purpose of my talk, this is interesting because it also shows evidence of an outflow, which is, however, inferred to be much weaker than the Swift event, with total energy orders of magnitude below that of the Swift. Okay, so let's think about how we could possibly explain this apparent dearth of jetted tidal disruption events. So there are two natural classes of explanations. So one is that for some reason jets are intrinsically rare, or powerful jets are intrinsically rare in tidal disruption events. And this could be because you need some sort of special conditions to launch the jet, which are rarely met in tidal disruption events. And speculatively, this could be because you need a large magnetic flux to power the Blandford-Zanaik mechanism. And generally, disrupted stars can't provide that level of magnetic flux. The second class of explanations is that jets are not intrinsically rare, but generally the density of the circumnuclear medium is too high or too low to produce observable synchrotron emission from the jet. And the density of the circumnuclear medium could affect the light curve peak and the light curve time. So in order to explore this possibility, we need to figure out a physically plausible range for the density of the circumnuclear medium. So in a galactic nucleus, we have lots of stars, and these stars are going to shed gas through stellar winds. And here's a nice illustration of that, which I stole from Nora Lutzendorf's website just because I thought it was cool. So yeah, and the other thing I want to show with this picture, besides that it's nice to look at, is that this process is likely to be quite complicated. You have to think about the fact that you have individual stars and they're moving around in complicated ways. So just keep that in the back of your head as I go to my spherical cow model. So we're going to take a simple model for the circumnuclear medium, and this is this is essentially the model in Quadrant 2004 for the galactic center, if you're familiar with that, and we also describe it in a recently published paper. Okay, so you have the black hole, you have a stellar population around it, injecting gas through stellar winds, and we're going to take a simple 1D spherical model. So gas can either inflow or outflow. At small scales we expect it would inflow, at large scales it would outflow. And at some characteristic radius, the velocity of the gas will pass through zero, and that characteristic radius depends on the black hole mass and the heating rate. Okay, let's see how the gas density, I'll start with inflow rate and then work towards the gas density. Let's see how the inflow rate and the gas density depend on the parameters of the problem. So the inflow rate is related to the stellar mass enclosed within the stagnation radius via a mass return efficiency, which depends on the properties of the stellar population, like the stellar age. If you have large massive stars, they're going to shed a large amount of gas through stellar winds. And to be concrete, I'm going to choose a particular stellar density profile to give you a concrete scaling. So I choose a cusp-like density profile for the stars. And Nick gave a nice motivation this morning for why about cusp and core stellar density profiles and why we expect the cusps to be more relevant for tidal disruption events. So to remind you, the cusp density, stellar density goes roughly as radius to the -2. I've chosen slightly shallower slope here. So it scales with black hole mass and mass return efficiency, and most sensitively with heating rate. So we already see that the heating rate is going to be quite an important parameter in this problem. From the mass inflow rate, we can estimate a gas density. And so here's a scaling relationship for that, again, for a cusp-like stellar density profile. So we see, again, the scaling with black hole mass, mass return efficiency. We generally find 1 over R density profile. And then the most sensitive scaling is with the heating rate. Okay. And so this is, now I'm going to show you a few examples of steady state gas density profiles we've solved for and how they vary with the parameters of the problem. So this shows a few different profiles for different black hole masses and heating rates. So if you look at the blue solid and orange solid curves, the blue solid is a higher heating rate, and this profile has a smaller stagnation radius. You have a higher heating rate, so you're blowing out more of the gas, and so the stagnation radius is at small radii. And then as you decrease the heating rate, the stagnation radius, the point where the velocity goes through zero, moves outward, and the gas density increases. Okay, this slide is essentially showing the same thing. I've just added the velocity profile. Right, so as I decrease the heating rate, the stagnation rate just moves outward, and I increase the density. Right. So let's think a little bit about the heating rate in galactic nuclei. So there are several potential sources of heating. So in particular, I'd like to highlight the role of young massive stars with fast stellar winds. So if you have a significant number of those could provide a significant heating source. The wind velocities for massive stars are going to be quite high, of order 1,000 kilometers per second. There are other sources of heating, also like 1A supernovae, and black hole feedback is another potential source of heating, which I'm not going to consider here because TDEs our existing TDE candidates are in inactive galaxies. And so just to explain a little bit of what's going on here, so for each black hole mass, I've taken a star formation history, an appropriate halo average star formation history, and at the low black hole masses, you have sufficient star formation to produce a significant number of young stars and provide a significant heating rate. Yes. See, so it's going to depend on the star formation rate. So it's a convolution of the star formation rate and the delayed time distribution. Right, so the star formation rates are taken from abundance matching models, and essentially for each black hole mass, we want a star formation history that would produce a bulge consistent with the MBHM bulge relationship. And we take a halo averaged abundance matching star formation rate for that, right? And then we convolve that with, for the 1As, we convolve that with the delay time distribution. Yeah. Is there another question? No. Okay, so let's think about the overall range of densities we can produce in the circumnuclear medium. So here I'm considering the space of heating rate and mass return efficiency. So I've fixed the black hole mass of 10 to the 7 solar masses and a cusp-like density profile. So here I have contours of constant density at 10 to the 18 centimeters. If you've forgotten what the mass return efficiency is, you can look here. It just relates the stellar density to the injection rate of gas mass. Okay. So one thing that is important to think about is if you decrease the heating rate of the gas too much, it'll become thermally unstable, condense into cold clumps, and we're most interested in the density of the volume filling hot phase of the gas. So we ignore regions of the parameter space which would be thermally unstable. So that's below this black line here. And now we're going to consider different extreme star formation scenarios to see what range of gas densities we can get. And here we're just trying to see what is the most extreme range we can get in our formalism. So at the high density end, we can consider a stellar population just a few mega years after a starburst. Now here you have massive stars shedding a lot of gas through stellar winds and a very high mass return efficiency of order 100. And you get a density of order a few thousand particles per cc. And then, okay, so that's roughly the highest density we can get. Yes. Really? I'm at 14. Okay. Oh, okay. I thought it was 6. But okay. Well, okay. But now let's consider the low density end. So here we consider a mix of an old and a young stellar population. So if you have old stars, the mass return efficiency is quite low. So this is, if you just have the old stars, you would be here. And then as you add young stars, you increase the heating rate. Eventually, you also increase the mass return efficiency, taking you to high densities. But in the middle, you have a sweet spot where you have a high heating rate and a low mass return efficiency. And so you get a low density of order 0.1 particles per cc. Now, both these scenarios are somewhat contrived, involving bursts of star formation. The point was just to sort of see what the most extreme range we get. And in this case, I'm being particularly generous because if you consider the fact that the real stars are discrete, this scenario is sort of this scenario is difficult to realize physically and could require fine tuning. Perhaps one effect that could lower the density in real systems. So recall we're considering a spherical cow. Potentially, you could have stars in some kind of disk arrangement, which could lower the density. And this is a scenario considered in NIACTION 2005, and in that particular case was found to be about an order of magnitude effect. So roughly, we find a range of gas densities around 0.1 to 1,000 particles per cc. Okay, so great. So now, why did I do all this work? Oh yeah, we want to see if we could hide jets. So now we're going to take a jet model, and this is a model that was used to fit the radio data for the Swift 1644 event. And we fixed the jet properties to be the same. And I'm going to gloss over the details. This is the jet energy. And then the structure of the jet is somewhat complicated. You have two components, a fast core and a slow sheath. Fast meaning gamma of 10 and slow meaning gamma of 2 initially. And the reason you need the two components is to explain why the radio emission stays bright for as long as it does. So we're going to fix the jet to be the same and then see how the radio emission would vary as we vary the density of the circumnuclear medium. So here I look at 3 different density profiles and look at the calculated light curves at 5 gigahertz. Right, and I've also plotted the same upper limits from before for tidal disruption event candidates. And we see for a broad range of circumnuclear medium densities, we get quite bright radio emission, and for all these choices of density, it falls above these upper limits. So these, to be clear, these are on axis, but at least for the 2 high density cases, we've checked that looking at an off axis makes at most a factor of a few difference. And then to be really sure that you can't hide the density emission, we should think more carefully about this low density limit. This is sort of what's most important in concluding whether you can realistically hide the radio emission. Okay, and then another thing to point out is that the peaks of radio emission, particularly at low densities, are at quite early times, which suggests we need prompt. It would be nice to get prompt follow-up for tidal disruption event candidates to constrain jets. Okay, so now I'll just go to my conclusions and summary. So we've come up with a range of plausible gas density. Oh, I should have said, so this is at a scale of 10 to the 18 centimeters, so that's important. So at a scale of 10 to the 18 centimeters of 0.1 to 1,000 particles per cc, we find bright radio emission for a wide variety of density profiles, not quite to 0.1 particles per cc, but it's not clear yet whether that's even a physical scenario. And so given the existing upper limits, and our light curves, this suggests that swift-like jets are not present in most tidal disruption event candidates. And so the implication of this is that swift-like jets are intrinsically rare in tidal disruption events. Okay. So. James?
So in the case paper with the outflow of 14 Li, he derived the background density was really quite low, like 10 to the minus 2, I think, at maybe 10 to 17, maybe something like that.
Yeah.
And so I think it'd be even lower at 10 to the 18.
That's right, if that were true, yes.
Looking at your curves, the lowest density one you plotted was 2, and it looks like that you considered up to 10 to the minus 1. So does that suggest that we should expect in very low density environments very prompt flares, like even prompter than the ones we showed? And I would think that would actually put them above the upper limit for some of the, like when you pull up your plot, the light curve on it. Yeah. Right, so if I take the 2, and I imagine like another curve in that sequence to the left of the 2 tick, that it would actually cross below some of those other limits.
Okay. Well, first I want to comment on the low density. So I think there's a sort of a degeneracy in modeling the radio emission, and that's not a unique fit for the radio data, as I think Short will talk about later. And then the other thing that makes me doubt the low density is that the 14 Li event was in a galaxy which showed evidence of previous AGN activity, which I would expect would indicate a higher density. But okay, back to, so if I considered an even lower density, you're saying I would have prompt emission?
Well, you'd have prompt emission, but the curve, like the
Yeah.
tail, they would actually go below some of the black upper limits.
Yeah, no, that's true. So if you continue, I mean, if you take the density to 0, the emission,
Yeah.
like
Yeah. You're basically taking those curves and just shifting this way.
right. That's right. That's yeah.
So now it's about moving on. This analysis is a vector partition analysis. It's the one that was studied. And vector partition analysis assumes that in languages, gamma ray to the subset mode, that epsilon b is 1 and epsilon e is 1. And if you change these two parameters, then you discover that the value that you get for b and for e are just upper limits, lower limits. So it can be anything above it. So to state that this is robust measurement is a big thing to say.
Yeah, I can comment on that more when I give my talk, but I would agree with what Steve just said, that what we wanted to highlight about our density profile is more the radial dependence and less the normalization, which, as we said, it does depend on what you assume fraction of the less field is, and it depends somewhat on what you assume geometry in the outflow is. If you assume that there's an interface with this or a tone, then that also can lead to normalization. So yeah, it'll be interesting to discuss if you have other ideas about why it would be lower.
The thing which is sort of robust from this estimate is the radius.
Yeah.
So since the partition is very sensitive to the radius. So
Yeah,
if
you
you
get a
find the
very good
radius, you
estimate
cannot
of
change the
radius.
radius very much.
Yeah, you get a very good estimate of radius.
But
You get a
for
good estimate. The energy doesn't depend much on the geometry of the outflow, but it does depend on how much energy the electron is transferring.
So do you still think that the debit bill is unsustainable? So what's going on with the debt evolution?
I think, yeah. Yeah, I'm not sure what the Lorentz factor is. I don't think it's certainly dominated by the slow component at that point.
In 1644, the latest time, the jet was, the highest Lorentz factor was definitely less than 2.
Yes.
It was most likely non-relativistic, but it was definitely not more than 2. And with Lorentz factor of 2, you can forget anything that you know about feeling. So things are effectively isotropic. So you can have extremely narrow jet and still see as wide as possible because the emission will not be dim. So
That's taken into account. But I also had a remark then on James' point, not related to 14Li, but that these curves are for an interacting jet still, right? So if you keep decreasing the density at some point, the jet is like a train and it just goes through, and then you go into a different regime where you can have internal shocks, much more similar to AVN jets. So that would be a floor that you hit. And these limits would still be inconsistent with those types of jets in a vacuum. Although there the Dr. Boostering is more significant. But for most viewing angles, these limits would be inconsistent with jets in a vacuum as well.
It depends on gamma. If your gamma coefficient is large and you're doing it at a large angle,
Yeah. But then you compute the probability that all of them are, at a disfavorable angle, and then you can rule out the hypothesis that all of them are. Unless gamma is 10. So you rule it out for given gamma. So for gamma lower than 5, you can rule out those hypotheses.
1644, the initial Lorentz factor is about 10 to 16.
you said that the jet will only occur if the density of the separation is within a certain range. But you calculated the gas density, not the density of the system.
What I calculated, I'm calculating the ambient gas. That's right. No, of course, right. What do you mean exactly by the, like, on what scale are you considering the TDE gas, or like the molecular ring? Yeah. Right. Right, yeah, so that's a good point. So I guess that's fairly significant solid angle. But I mean, it doesn't cover complete, right?